energy which is the radiant energy which is transmitted through space at enormous velocity. So that means, so that is one type of radiant energy, and that is transmitted in space. So it exists in various forms, that is the visible light, radiant heat being easily recognized from which we experience in day-to-day life, and the electromagnetic radiation, unlike sound, does not require any medium for transmission and pass readily through vacuum. So for electromagnetic radiation, we need for transmission of electromagnetic radiation, no medium is required, and in vacuum, the velocity of electromagnetic radiation is similar to the velocity of light, that is 3 into 10 to the power 8 meter per second. Now coming to wave mechanical model of electromagnetic radiation. So here we will discuss the wave mechanical model of electromagnetic radiation. You can see the electromagnetic radiation is considered to be sinusoidal in nature, that is just like the sine wave, that is varying like a sine function. Now, according to Maxwell's theory, an electromagnetic wave can be visualized as oscillatory electric and magnetic fields traveling in planes perpendicular to each other and also perpendicular to the direction of propagation. That means the electromagnetic radiation contains two perpendicular vectors, one electric field vector and magnetic field vector, that contains both the electric field and magnetic field vectors, both are perpendicular to one another, and also they are perpendicular to the direction of propagation. However, since it is theoretical effect, it is responsible for the phenomenon of interest of chemists. So you can see from this image. So this is the image of an electromagnetic radiation. So now let this is the origin. So the electromagnetic radiation traveling, and this is the direction of propagation. So you can see the electromagnetic radiation contains two components. One is electric field vector and the another one is magnetic field vector. Both the components are perpendicular to one another. And after that, we will discuss the characteristics properties of electromagnetic radiation. So, so the electromagnetic radiation characterized in terms of different parameters. So the first parameter is amplitude. So first we will discuss what is amplitude. Now it refers to the maximum height to which the wave oscillates and equals to height of the crest or depth of the trough. So electromagnetic radiation travels, electromagnetic radiations having wave like nature. So it has wave like nature. So the property of the electromagnetic radiation are similar to the property of the wave. So here we are discussing the characteristics properties of electromagnetic radiation. So first one is amplitude. You can see, suppose this is one wave. This is the wave. This one is the wave. So we know that so this is a complete wave. Now for a complete wave, one crest is there and one trough is there, and this complete wave is called one cycle also. So that is called one cycle. So in a complete wave, when one crest is there and one trough is there, so the maxima point is called crest and the minima point is called trough. And the height of the crest or depth of the trough is known as amplitude. So this is the height of the crest and this is also the depth of a trough. This is known as amplitude. So for a complete wave, there will be two consecutive crest and trough. So the height of the crest or depth of the trough, that is known as amplitude, and it is measured in the radiant power of the radiation. So the radiant power refers to energy of the radiation striking at a given area per unit time. It is denoted as P and is related to square of the amplitude. So it is important to remember that the radiant power is not related to wavelength. So that means the radiant power is related to amplitude, and the radiant power is denoted as P, which is equals to a square of amplitude, and it is closely related to intensity of the radiation. That means the wave having more amplitude, having more intensity, which is denoted as I, and is defined as the radiant power per unit solid angle. So this is the first characteristics, and next we'll move to the second characteristics. So the second characteristics is wavelength. So here you can see, suppose this is one wave. So in wave, one crest and one draw is there. That is, and let this is the direction of propagation. So this wave is called one cycle or a complete wave. That means that should contain a complete crest and complete draw. That is called a complete wave, or that is called one. So this is one cycle. And similarly, let this is the direction of propagation. This is the direction of propagation, and the wave will travel like this. From left to right, that is the direction of propagation. So now, what is wavelength? So the wavelength is the distance between two consecutive crests. So this is the distance between two consecutive crests, or the distance between two consecutive draw. That is known as wavelength. The distance between two consecutive crests or the distance between two consecutive draw, that is known as wavelength, and it is denoted as lambda. So this is known as wavelength. And it is also, we can also define the wavelength as the distance of a complete wave. All are same. The distance between two consecutive crests and the distance between two consecutive draw, that is called lambda. The distance between two consecutive crests is called lambda wavelength, and the distance of a complete wave, that is also called wavelength lambda. So as this is the distance, so the unit of wavelength should be the unit of distance, that is meter, centimeter, micrometer, nanometer, angstrom, etc. So the wavelength of electromagnetic radiation varies from few angstrom to several meters. And here, so the conversion is there between the different units of distance. One uh, 1 meter equals to 10 to the power 9 nanometer. 1 meter equals to 10 to the power 9 nanometer. And similarly, in the reverse way, we can say that 1 nanometer equals to 10 to the power minus 9 meter. And similarly, 1 meter equals to 10 to the power 10 angstrom. In the reverse way, we can say that 1 angstrom equals to 10 to the power minus 10 meter. Similarly, 1 meter equals to 10 to the power 6 micrometer, that is called mu m. In the reverse way, we can say 1 micrometer equals to 10 to the power minus 6 meter. So these are the different units of wavelength. Now coming to the next one is frequency. The next one is frequency. Now frequency, it is defined as the number of wave crest or wave troughs, or the number of complete waves passed through a given point per second. Suppose this is the direction of propagation of the wave, and here we will put a marker. One marking position is there. So at that mark, so suppose this is the marking position along the direction of propagation of the wave. So along that marking position, the number of complete waves passed through that marking position per second is known as frequency. Again, I am repeating, the number of complete waves passing through that specified point per second is known as frequency. So that means if the wavelength will be less, then the number of complete waves passed through that particular point will be more. That means the frequency is inversely proportional to wavelength. And if the wavelength will be more, then the number of complete waves passed through the particular point will be less. So it is defined as the number of crests or number of troughs, number of wave crests or the number of wave troughs, or the number of complete wave. That means the number of cycles passed through a particular point in 1 second, or given point per second, that is known as frequency. It is represented by a Greek letter nu and is expressed in terms of second inverse or per second or cycles per second, CPS, that is called cycles per second, or the number of waves per second. So that's why the unit is second inverse. You can tell second inverse, you can tell cycles per second, CPS, or that is also equals to hertz. That means 1 hertz equals to 1 second inverse equals to 1 CPS. So the relationship between wavelength and frequency is like this: nu equals to c by lambda, where c equals to velocity of light, which is the velocity of the electromagnetic radiation in vacuum, that is equals to 3 into 10 to the power 8 meter per second. That means the velocity of any type of electromagnetic radiation is generally considered to be 3 into 10 to the power 8 meter per second. Now coming to the next property, that is called wave number. So wave number, it is equals to number of waves per centimeter or per unit distance. Now suppose this is the direction of propagation of the wave and this is 1 centimeter distance. So in 1 centimeter distance, the number of complete waves or complete cycles present is known as wave number. That means it is the reverse of wavelength. So it is just the reverse of wavelength. That means if the wavelength will be less, more number of complete waves will be present within that unit distance, and it is denoted as nu bar and is equal to reciprocal of the wavelength, and it is expressed in meter inverse. So the unit of nu bar is meter inverse, and also sometimes it is also expressed in centimeter inverse, which is commonly employed unit. Now coming to the velocity, next characteristics of the electromagnetic radiation, that is called velocity. It is defined as the linear distance traveled by the wave in 1 second. So just like object travel per second, that is called velocity, it is also defined as the linear distance traveled by the wave in 1 second, and the velocity in meters per second can be obtained by multiplying the frequency in second inverse by wavelength in meters. That means velocity equals to frequency into wavelength. So frequency means the number of waves or the number of complete waves passing through a point in 1 second, and wavelength means the distance of a complete wave. So that means, so that is nothing but the distance traveled by the wave per second. So c equals to nu into lambda. Nu into lambda. So c is the velocity of the electromagnetic radiation, which is equal, so that is generally considered as for any type of electromagnetic radiation, the velocity is generally considered as 3 into 10 to the power 8 meter per second. So here c equals to nu into lambda, and hence nu equals to c by lambda. And the velocity of electromagnetic radiation depends upon the medium. It has the maximum value if the medium will be vacuum, then the maximum value of the velocity of electromagnetic radiation will be 3 into 10 to the power 8 meter per second. So that means that will be equals to the velocity of light. Now coming to the next characteristics property, that is energy. So the energy of electromagnetic radiation depends on the wavelength or frequency. We know that according to Planck's equation, E equals to h nu. So that is, again, if we write nu equals to c by lambda, so in place of nu we can put c by lambda. So E equals to h nu, that is equals to hc by lambda. So this equation, so in this equation, c is the velocity of electromagnetic radiation, that is considered to be 3 into, again I am repeating same thing, the c is the velocity of electromagnetic radiation, that is considered to be 3 into 10 to the power 8 meter per second. Lambda is the wavelength of the electromagnetic radiation, and h is the Planck's constant having the value. So you have to remember the value of the Planck's constant. So the h equals to Planck's constant having the value 6.626 into 10 to the power minus 34 joule second. So till now we have discussed these characteristics of electromagnetic radiation. So on a summary, wavelength is denoted as lambda and having common unit of distance, that is meter, micrometer, nanometer, angstrom, etc. And similarly wave number, that is nu bar, which is the reciprocal of lambda. So nu bar equals to 1 by lambda and having the unit meter inverse, centimeter inverse, etc. Then frequency, nu equals to c by lambda, and having the unit CPS, cycles per second, or second inverse, or hertz. And then coming to velocity, c equals to nu into lambda, and having the unit meter per second. And then energy, E equals to hc by lambda, and having the unit joule. Now coming to electromagnetic spectrum. So the if we'll arrange the different types of electromagnetic radiations according to increasing order of their frequency, or increasing order of their wavelength, or decreasing order of their frequency, or decreasing order of their wavelength. So the series will call electromagnetic spectrum. The series of spectrum obtained will be called electromagnetic spectrum, because we know that different types of electromagnetic radiations are there. So if we arrange the different electromagnetic radiations according to increasing or decreasing order of their wavelength or frequency, that is called electromagnetic spectrum. So here, so this is one electromagnetic. So this is the example of electromagnetic spectrum. You can see this is the example of electromagnetic spectrum, and in this figure you can see the electromagnetic radiations are arranged. Here in this figure you can see the electromagnetic radiations are arranged according to increasing order of their wavelength from left to right. So in this image, in the bottom you can see increasing wavelength. So that means the wavelength increases from left to right. So here the electromagnetic radiations are arranged according to increasing order of their wavelength from left to right. So increasing order of wavelength means that is decreasing order of frequency. So increasing order of wavelength means the left hand side will be have least wavelength, and the right hand side will be have highest wavelength. But if we tell in sense of frequency, so increasing order of wavelength means decreasing order of frequency. The electromagnetic radiations having least wavelength is having highest frequency. So the first one is gamma ray, having least wavelength, so the frequency of gamma ray will be highest. After that it will call X-ray, then ultraviolet, then visible, then infrared, then microwave, and then the radio waves. Again, the radio waves are divided into two types, that is radio waves and long radio waves. Again, the so radio wave again divided into FM and AM. So you can see, and here, so here different types of electromagnetic radiations are there: gamma ray, number 2 X-ray, number 3 ultraviolet, number 4 visible, number 5 infrared, number 6 microwave, number 7 radio waves. So out of the 7 electromagnetic radiations, we can see only the visible light. So the visible, so if we zoom the visible radiation, you can see here the wavelength ranges from 400 nanometer to 700 nanometer. So in this visible spectrum, you can see different colors, that is Vibgyor. So apart from this visible range, all the remaining electromagnetic radiations are colorless. Now coming to polychromatic radiation. So polychromatic radiation, we can generate or separate out radiation of a single wavelength from a polychromatic. So polychromatic radiation means the radiation which contains different types of polychromatic radiation means the radiation which contains electromagnetic radiation of different wavelength. But monochromatic means so radiation which contains a single wavelength. We can generate or separate out radiation of a single wavelength from a polychromatic radiation by using suitable device, that is called monochromator. So that means if we will pass the polychromatic radiation through a monochromator, so that will become monochromatic. Such a radiation is called monochromatic radiation. Now, so before going to the quantum mechanical model, we should discuss the origin of quantum mechanics, why quantum mechanics arise apart from the classical mechanics. So the first effect is black body radiation. So here we will discuss what is black body radiation. Now all heated objects emit electromagnetic radiation, and the wavelength of these radiations depend upon the temperature of the object. For example, at relatively low temperatures, a metal rod emits infrared radiation which we cannot see but feel as heat. Again, I am repeating, when the suppose we will heat one metal rod, so the metal rod emit infrared radiation which we cannot see, only we can feel the heat. As the temperature is again increased to 600 degrees Celsius, a dull red color is visible, and when the temperature will increase to around 2000 degrees Celsius, the metal rod glows white. So one can visit a blacksmith and observe the changes in the glow of iron as it is heated at higher and higher temperature. So this is one example. Hence, energy radiated by the hot surface depends upon its nature and surface area besides the temperature. For a given area, so if the area is fixed, for a given area and temperature, a black surface radiates more energy. So that means if the surface area is fixed and also the temperature will be fixed, a black surface radiates more energy per second than a polished surface. That means at a given temperature, the maximum radiation would be given out by a perfectly black surface. The experimentally observed data of radiation intensity emitted at a different wavelength by a perfect black surface at a different temperature could not be explained by classical mechanics. So whatever, before different types, the other mechanics that is known as classical mechanics. So the maximum wavelength emitted by the black surface cannot explain by classical mechanics, and this effect is called black body radiation. Now coming to another, so another effect, that effect is also coming to another effect, that effect is also cannot be explained by classical mechanics. So this effect is also explained by quantum mechanics. So as these different effect was so these different effects were not explained by classical mechanics, so that will give rise to a new mechanics that is called quantum mechanics. So now let us discuss the photoelectric effect. Hertz observed that when a light of appropriate wavelength fall on a clean surface of metal plate placed in an evacuated vessel, a stream of electron is emitted. So that means suppose this is a clean metal surface. So when light of appropriate wavelength will fall on the metal surface, so if the energy of the light fall on the metal surface is greater than equals to the energy of the is will be greater than equal to the energy of the that means the binding energy of the electron, then electron will be ejected from the surface. So that means electron will be emitted from the metal surface. So Hodge observed that when a light of appropriate wavelength fall on the clean surface of metal placed in the evacuated vessel, at stream of evacuated vessel, a stream of electron is emitted. These electrons are called photoelectrons. Because of these emitted due to light, a moving electron constitute electricity, and the phenomenon emission of photoelectrons is related to photoelectric effect. Alkali metals, because we know that for alkali metals, the outermost electrons are loosely bound electrons. Hence, for alkali metals having loosely bound electrons, so by fall of electromagnetic wavelength of approximately less energy, then the loosely bound electrons from the surface of the alkali metals will be emitted, and that is called photoelectric effect. Now, in quantum mechanics, in the quantum or particle model, the radiant energy is considered as a stream of discrete particles or packet of energy that is called quanta. So that means, in according to classical mechanics, suppose this is the metal surface, the radiant energy, suppose light will fall on the metal surface and energy will be emitted. According to classical mechanics, the radiant energy will be continuous, but according to quantum mechanics, the radiant energy will be discontinuous, so that will in the form of small quanta or small discrete packets of energy, that is called quanta. So that means discontinuous manner energy will be radiated in discontinuous manner or small packets of energy, that is called quanta. So these small packets of energy are called quanta, whose energy is proportional to its frequency, and it is related to E equals to h nu, and alternatively we can say E equals to hc by lambda, or again here in the denominator lambda is there, so that is also we can write E equals to hc nu bar. It is important to remember that the energy of the photon, it is important to remember that the energy of the photon is not same as the energy of radiant power, and the radiant power include the energy of the photon as well as the number of photons in the radiation. Now coming to an example, so in this example you see a microwave, so radiation having a frequency 12 gigahertz. What will be its energy of the photon corresponding to this radiation? Calculate wavelength of this radiation. So here, Planck's constant is given in this question, that may not given. So 1 gigahertz means 10 to the power 9 hertz. 1 gigahertz means 10 to the power 9 hertz, right? So here we know that energy E equals to h nu, and which is equals to h means Planck's constant, nu means frequency in so here 12 gigahertz means 12 into 10 to the power 9 hertz, that is 1.2 into 10 to the power 10 hertz, which is equals to 7.95 into 10 to the power minus 24 joule. So the energy of the photon having a frequency of 12 gigahertz equals to 7.95 into 10 to the power minus 24 joule. Further, since E equals to hc by lambda, we can rearrange lambda equals to E by hc. So by this we can find out the wavelength of the electromagnetic radiation, that is lambda equals to 7.5 into 10 to the power minus 24 joule divided by Planck's constant into c means velocity of light. Calculating this, we can find out lambda is 400 nanometer. Now coming to the consequences of wave nature of electromagnetic radiation. So these are the consequences. Consequences means as the electromagnetic radiation having wave nature, that is not having particle nature. So as the electromagnetic radiations are having wave nature, so due to the wave nature of electromagnetic radiation, what are the consequences? So here the first one is interference. Interference means Thomas Young reported the result of his famous double slit experiment of light. He observed that when a monochromatic light was made to pass through two closely spaced narrow slits to fall on a distant screen, a series of dark and light bands are observed. So, 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 so here this is a monochromatic light, and here the monochromatic lights are passing through two narrow slits, and here this is the reflecting screen, and sometimes you will see the wavelength of the monochromatic light will merge. So if the wavelength of the monochromatic light will merge with one another, so that will form constructive interference, and so that the resultant wavelength will increase. And so suppose this is one wave, first wave, and this is the second wave, and now if you merge the first and second wave, the amplitude of the resultant wave will be increased, that is called constructive interference. Now suppose this is the first wave and this is the second wave. Now if we merge the two waves, the resultant amplitude will be decreased. So this type of interference will be called destructive interference. So here the schematic representation of interference of wave. So this is constructive interference. The wavelength will increase, the resultant wavelength will increase, and this is destructive interference. And this is partial constructive and partial destructive. Now the other phenomenon that is called a diffraction. So these are the few characteristics of electromagnetic radiation, as the electromagnetic radiation having wave nature. So due to its wave nature, so these are different characteristics of electromagnetic radiation. Now we will move to our main part, that is called interaction of electromagnetic radiation with matter, that is known as spectroscopy. So spectroscopy is the study of interaction of electromagnetic radiation with matter. So that will discuss the interaction of electromagnetic radiation with matter. Now, the quantum mechanical description of electronic structure of atoms or molecule consisting of matter, that these have unique set of quantized energy states available to them. So because we know that for atoms and molecules, unique set of quantized energy levels are there. So if if you consider atom, the quantized energy levels are K, L, M, N cells, etc. And if we consider a molecule, so the molecular energy levels are there, just like sigma 1s, sigma star 1s, sigma 2s, sigma star 2s. That means bonding and antibonding molecular energy levels are there. So all these energy levels are quantized. So these arises from the motion of electron around the nucleus, and the electrons in an atom and molecules are present in the allowed or permissible energy states only. However, in case of molecules, the rotation and vibrational motions are also quantized. That means if we if we consider atom, single atom, so if we consider single atom only, the different energy levels will arise due to motion of the electron around the nucleus, due to motion of electron around the nucleus. That means electronic transition will be there. So if we consider only atom, electronic transition will be there. That means the electron will move in different energy levels, different quantized energy levels. But however, if we consider molecule, apart from this electronic motion, rotational and vibrational motions will be also there, because in molecules different atoms are bonded with one another, and this bond will rotate around its new internuclear axis, and there will be bond vibration. So in case of molecules, apart from this electronic transition, rotational and vibrational motions are also there, and hence, just like electronic quantized energy level for atoms, similarly for molecules, apart from the electronic quantized energy levels, rotational and vibrational motions are also quantized in addition to these electronic energy levels. So the allowed energy levels with least energy is termed as ground state, while the rest are called excited state. So this is, you can see, so this is the schematic diagram showing the energy levels of a molecule. So here, this is the rotational energy levels. So the first one is the electronic energy. So the first one is the vibrational energy levels. So this is the vibrational ground state energy level, and within that vibrational, different rotational energy levels are there, and this is the first excited state. So the first one is the ground state electronics energy level. So within the ground state electronics energy level, the molecule can undergo rotation and vibration. So within the ground state electronic energy level, there will be vibrational energy levels and also rotational energy level. So this is the first excited state electronic energy level. So within that first excited state electronics energy level, there will be ground state energy level, there will be rotational energy level and vibrational energy level. Similarly, for second excited state also. Now, the energy difference between two energy levels, that is del E equals to E2 minus E1, where E2 is the energy of the higher energy level and E1 equals to the energy of the lower energy level. So, del E equals to E2 minus E1, that is equal to h nu, where h is the Planck's constant. Nu is the frequency of the frequency of electromagnetic required for transition of that electron or particle from one energy level to another energy level. Now coming to absorption. So that means when the particle will absorb energy, that will undergo transition from lower to higher, and if that will emit energy of particular electromagnetic radiation, that will come back from higher to lower. So the first one is absorption. At a given temperature, different species, that may be atoms or molecules, are distributed among the allowed energy levels in accordance with the Boltzmann distribution. Now, according to Boltzmann statistical distribution, the population of the ground state, that is the number of species in the ground state, is highest, and it keeps on decreasing as we move to higher energy level. Suppose this is the ground state, so the first excited state, second excited state, third excited state. So the population means the number of particles or the number of atoms or the number of molecules. The number of molecules present in the ground state will be always high, and the number of molecules present in the successive excited state will gradually decrease. Now, the population of any excited state relative to that of the ground state can be given according to the formula Ni divided by N0. N0 means the number of molecules present in the ground state. Ni means the number of molecules present in any excited state. So Ni by N0 equals to e to the power minus del E divided by Kt. Ni and N0 are the populations of the ith level and the ground state level respectively. And del E is the difference of amount of so del E is the difference in energy of the ground and excited state. K is called a Boltzmann constant, and again you have to remember the value of the Boltzmann constant, that is 1.38 into 10 to the power minus 23 joule per Kelvin. I am repeating that one. So the value of the Boltzmann constant, that is 1.38 into 10 to the power minus 23 joule per Kelvin. So here one question is there, you can see, let us calculate the population of an energy level having energy 2 kilojoule per mole relative to the energy of the ground state at 300 Kelvin. Again I am repeating that question, let us calculate the population of an energy level having energy 2 kilojoule per mole relative to the energy at the ground state at 300 Kelvin. So here del E equals to EF minus EI. EF is energy of the final state or excited state. EI is the energy of the ground state. So which is equals to del E equals to 2 into 10 to the power 3 joule per mole. So here it is given the difference, that is 2 so del E, so that is 2 kilojoule per mole. So that means 2 into 10 to the power 3 joule per mole divided by Avogadro's number. Why that is Avogadro's number? So it is given per mole, but here we are counting the energy difference between two energy levels per atom or per species. But here it is given per mole, 2 kilojoule per mole. That means 2 into 10 to the power 3 joule per mole divided by 6.022 into 10 to the power 23. So which is equals to 3 into 32 into 10 to the power minus 21. So this is the energy difference between ground state and excited state energy level of a particular atom or particular species. Now, for this particular atom, for this particular species, this is the energy difference. But according to the question, let us calculate the population of an energy level. So that means in a particular energy level, how many atoms will be there? Now, according to the Boltzmann distribution equation, Ni divided by N naught, Ni divided by N0 equals to e to the power minus del E divided by Kt, which is equals to e to the power, the value of del E here, so we have calculated the energy difference and e to the power, so we have calculated the energy difference, and here this is the Boltzmann constant, and here T means 300 Kelvin. So after solving this, we can find e to the power minus 0.802 by using scientific calculator. You can find the answer. This will be the answer. Now coming to continue. So here we are discussing the absorption spectrum. So in the absorption spectrum, two different types of absorption spectrum will be there: continuous absorption spectrum and discontinuous absorption spectrum. Let us see what happens when a polychromatic radiation is made to impinge upon a sample containing atoms or molecule. One simple possibility is that it gets transmitted unaffected through the sample. The other possibility is that the radiation coming out of the sample, the radiation coming out of the sample is devoid the certain frequencies. In the latter case, the missing frequencies are said to be absorbed by the sample, and only these photons are absorbed whose energy matches with the energy difference between the two energy states of the sample, provided that the transition among this energy level is allowed. Suppose here this is the source of electromagnetic radiation and that is passing through a sample. Now this is the source of electromagnetic radiation. So the source of electromagnetic radiation will pass through a sample, that will pass through a sample of organic compound here. Now you can see according to the characteristics of the molecules present in, so that will absorb one or two or some particular wavelength of electromagnetic radiation. Now after passing through the sample, so in this electromagnetic radiation, that will not find of that particular wavelength. So here in figure 1.1a, in figure, yes, this one. So this is the observing species. Now observing species is not there, so here we will find continuous spectrum. That means continuous spectrum means all type of electromagnetic radiation will be present here, but here some observing species is there. So that means before now here in the first case, you see in the first case, so this is the source of electromagnetic radiation. This one is the source of electromagnetic radiation, and that electromagnetic radiation will pass through a nickel prism, so that will give rise to electromagnetic spectra. So here in this electromagnetic spectra, you will find there will be all the you will find different electromagnetic radiations arranged according to increasing order of their wavelength or decreasing order of their wavelength. That means so there will be a continuous spectrum, no missing wavelength will be there. But when same electromagnetic radiation will be passed through some absorbing species, that means will be passed through some chemical, the solution of some chemical compound, then according to the nature of this chemical compound, they can absorb two or three electromagnetic, two or three electromagnetic radiations of particular wavelength, of which wavelength, the wavelength which will matching to their characteristics. So if as the sample present in the observing species will absorb electromagnetic radiation of some particular wavelength, that means, and after that when the electromagnetic radiation will pass through nickel prism, so in this electromagnetic spectra you can see some black lines will be there. Black lines means these electromagnetic radiations of particular these frequency are missing from this spectra. So that's why this is called discontinuous spectrum. These are called discontinuous spectrum. Now next one is atomic absorption. So atoms in the gaseous state can absorb ultraviolet or visible radiation or X-ray and result in a spectrum consisting of number of very sharp absorption lines that characteristics of the atomic spectra. So this is called a line spectrum. Now let us consider simple case of absorption of by gaseous sodium atom. So it exhibits two sharp absorption peaks in the yellow region of the visible spectrum. So the sodium atom will absorb two electromagnetic radiation having wavelength 589 nanometer and 589.6 nanometer. So as shown in this figure. So the consequence of so why the sodium atom will absorb electromagnetic radiation of particular two wavelength. So that is due to excitation of the 3s electron to two of the 3p states. So absorption in the UV region, on the other hand, result a signal at 330 nanometer and 285 nanometer due to excitation of the 3s electron to 4p and 5p states. So that means if the sodium atom will be excited by visible spectrum, that will absorb two electromagnetic radiations, one at 589 nanometer and other at 589.6 nanometer. So that is due to excitation of the 3s electron of sodium to 3p state. And similarly, if the sodium atom will excited through UV light, then that will absorb electromagnetic radiations of wavelength 330 nanometer and 285 nanometer due to excitation of 3s electrons to 4p or 5p orbital. Now coming to, so this is atomic absorption. Now coming to molecular absorption. So in case of molecules, the vibration and rotational motions is also quantified. So in case of atoms, only the electron will excite from lower to higher energy level, or from higher to lower energy level. So from lower to higher energy level in case of absorption, and from higher to lower energy level in case of emission. But if we consider molecule, in case of molecules, the vibration and rotation motion is also quantized. So in case of molecules, apart from this electronic transition, you can also observe vibrational and rotational energy levels. So in case of molecules, the vibrational and rotational motions are also quantized in addition to electronic motion. The molecular energy level, in fact, that is having three components, and its energy can be given by any of the by the following expression, that is the total energy equals to component of its electronic component plus its vibrational component plus its rotational component. So accordingly, three types of quantized transitions occur. Accordingly, three types of quantized transitions occurs on excitation with radiations in UV visible or in infrared or in microwave region respectively. The ultraviolet and visible radiations cause transitions of element from low energy electronic state to high energy electronic state. On the other hand, the IR and microwave radiations causes transition among the vibrational and rotational energy levels. So that means, so based upon this, you can find different types of spectra. Since the electronics energy level is associated with several vibrational energy levels, also each of the vibrational energy level is associated with several rotational energy levels also. So the transitions caused by UV visible radiation have associated with vibrational and rotational transition also. Accordingly, the molecular spectra are quite complex and consist of a large number of transitions. For this reason, the electronic absorption bands of molecules are usually broad and the spectrum is called band spectrum. So here in the figure 1.13 gives a simplified energy level diagram for a molecule showing the region of observing band spectrum And similarly, the transition caused by the radiation of higher region having an associated rotational spectrum component also. So this is the ground state electronic states, ground electronic states, and this is fast excited electronic state. Now you can see within the ground electronic states different vibrational energy levels. So within the ground electronic state, this is the ground vibrational energy level. This is the fast excited state vibrational energy level. This is second excited state vibrational energy level, and this is third excited state vibrational energy level. And similarly, within the excited electronic state, there will be also different vibrational energy levels. So within the excited electronic state, this is the ground vibrational energy level, this is the first excited vibrational energy level, this is the secondary excited vibrational energy levels, and so on. So here we have discussed, so due to this we have discussed UV visible spectra, then IR spectra, and then microwave spectra. Now apart from that, some other type of spectra are there. So that is due to magnetic field induced absorption. So the elementary particles such as electrons and nucleons are associated with magnetic properties. We know that electrons and nucleons are associated with magnetic properties because they are charged particles. They are circulating around their own axis. So due to that, magnetic fields are arises. So when subjected to external strong magnetic field, the interaction between the internal and external magnetic fields give rise to additional quantized energy level. The energy difference of these energy levels are small, and the transitions are brought by absorption of this radiation of longer wavelength range. So the transition among the energy levels generated due to interaction of nuclear magnetic moment with applied magnetic field are studied using radio waves in the range around 30 to 500 megahertz, and that will give rise to nuclear magnetic resonance or NMR spectroscopy. And similarly, the energy separated by the levels created by interaction between the electromagnetic movement of with applied external field is even smaller. So these are quite so these are studied under electronic spin resonance or ER spectroscopy. So now the fate of the absorbed radiation. So what will happen when the molecule will undergo absorption? As a consequence of absorption, the energy of the photon is transferred to the absorbing species and it acquire the excited state. So suppose this is the absorbing species, so the energy of the photon having energy h nu is transferred to the absorbing species. So this one is the absorbing species, and h nu amount of energy will be added or transferred to the absorbing species. And now after absorbing that, the species will undergo to excited state. So that is M star excitation. So the concentration, after that, the concentration of the excited species is so obtained is quite small and its lifetime is very short. So the excited species generally loses extra energy to the other atom or the molecule present in the medium and revert back to the ground state. This process is known as non-radiative relaxation. Occurs in a short period of time, that is around 10 to the power minus 6 into 10 to 10 to the power minus 10 seconds. So that means from the excited state, the molecule come back to comparatively lower energy levels by emitting energy lower or ground state by emitting energy none other than so radiation, that is called non-radiative relaxation. Relaxation means coming back from the excited state to ground state. So the excess of energy is transferred in a series of small steps to the neighboring species as their kinetic energy and is manifested in the form of heat. As a consequence of this, the temperature of the system increases slightly. So that means if the excited molecule will transfer its energy to its neighboring species, then its energy will be so the kinetic energy. So the kinetic energy will yeah, of the neighboring species will increase, and also so that will manifested in the form of heat. As a consequence of temperature of the system increases slightly. So this is the excited molecule that will come back to the ground state by emitting heat. That process is called relaxation, and this is non-radiative relaxation. And so the non-radiative relaxations are not generally associated with spectroscopy. In some cases, the relaxation process is accompanied by emission of radiation and is referred to as radiative relaxation. Now coming to emission. So during the festive season at the time of celebration, you must have enjoyed the beautiful display of colors, firework in the sky. So this splendid, so are the results of relaxation of excited species from higher energy level to the ground energy level, releasing excess amount of energy in the form of light and heat. So the colors we see are electromagnetic radiations in the visible range, and the excitation of the species can be brought about by a number of ways, such as absorption of electromagnetic radiation, bombardment with electrons or other elementary particles, exposure to the high potential alternate current, spark, arc, or flame, etc. So due to this, the molecules will undergo excited state, and again they will come back to the ground state by emitting different lights which falls in electromagnetic radiation, and the radiation emitted by the excited species is characterized by emission spectrum. Like an absorption spectrum, the emission spectrum can be band spectra, can be line spectra. So band spectra, suppose this is one excited sample and that will emit electromagnetic radiations. Now if you pass this electromagnetic radiation through this nickel prism, so that will split into different, that will split into one electromagnetic spectra. And here you can see, if this molecule will not emit, then the background of the photographic split photographic plate will be black, and as it is emitting, as the excited sample emitting electromagnetic radiations of particular wavelength, so at that wavelength you will find a bright line on the background of a dark screen. So that is called emission spectra. So the line spectrums are a result of relaxation of atoms or ions, and generally consist of a series of well-defined lines characteristics of the species involved. On the other hand, the band spectra, which consist several groups of lines that are closely spaced and not resolved, and are given by excited molecules or radicals. So in case of incandescent solid, we get continuous spectra wherein the line spectra and the band spectra are superimposed to appear continuum. Now coming to the line spectra are obtained from individual atoms that are well separated in the gaseous sample of an element, and the atomized sample of an element is subjected to flame or plasma or electric arc or spark, whereby constituent atoms are excited to higher orbital. For example, in case of sodium atom, single outer the single outer electron in the 3s orbital can excited to the higher orbital, the excited state being unstable and short-lived, so return to the ground state by emission of a photon, and the emission from the first excited state 3p of the sodium atom is responsible for the yellow color emission at 589.6 nanometer of the flame, and when the sodium salts are introduced in it. And the other excited states, the other excited states corresponding to 4p and 5p energy levels, so that will give emissions at 330.6 nanometer and 285.3 nanometer. respectively in the ultraviolet region. So the flame of emission and so the flame emission and atomic emission spectroscopic techniques are based upon this phenomenon and are useful for qualitative and quantitative measurement of atoms. So in the case of sodium, you can see that when the sodium atom will be excited, initially the sodium atom will be excited by emission of initially the sodium atoms present in the sample will excited due to flame, and after that the electrons which was initially present at the ground state energy level, that is at 3s energy level. So the outer electron of the sodium initially present in 3s energy level, so due to the flame, they will excite into higher energy level. So that means they will undergo excitation from 3s to 3p, and we know that in the excited state the lifetime of the electron will be very less. So again that will undergo relaxation by emitting electromagnetic radiations of particular wavelength, that is called radiative relaxation, and that will come back again to the ground state by emitting electromagnetic radiation of a particular wavelength. So if the electron will come back from the 3p energy level to 3s energy level, so that will emit electromagnetic radiations of 589.6 nanometer, which fall in the visible region. So that's why that will looks like yellow color. And similarly, if the electron present in the sodium atom will excited to some higher energy level, that is 4p or 5p energy level, and when that will again come back to the ground state by emitting electromagnetic radiations at 330.6 nanometer or 285.3 nanometer, so they will fall in the UV region. Now coming to band spectra. So the band spectra arises from gaseous radical or small molecules and consist of a series of closely spaced lines. So that's why that is called band spectra, that arises from the radiative relaxation of excited molecule any of the available vibrational energy levels in the ground state. Generally, so the band spectra arises from gaseous radicals or small molecules. So when they will undergo radiative relaxation process of the excited molecule to any one of the available vibrational energy level. So you can see, so suppose this is the ground state electronic level, this is the first excited state electronic level, and if the molecule will undergo excitation from ground state electronics level to first excited state electronics level, and after that here the lifetime will be very short, so they will come back to the ground state again. So in the ground state different vibrational, a series of vibrational energy levels are there. So this is the ground electronic state. So these are the vibrational energy levels, series of vibrational energy levels in the ground electronic state, and they can come back to the ground state electronic state and ground state vibrational energy level. They can come back from excited to ground electronic state and fast excited state vibrational energy level. Similarly for second, similarly for third, fourth. So a series of lines will come. So that's why that is called band spectra. Now coming to continuous spectra. The continuous spectra are caused by solid when heated. It is the characteristics of the temperature of emitted surface rather than the bulk of the material. These type of spectra are produced by condensed solid, giving rise to atomic or molecular oscillations. So heated solids are used as radiation source in the analytical instrument involving infrared, visible, and longer wavelength UV radiations. Now coming to fluorescence and phosphorescence. So in the emission spectra of atoms and molecules discussed above, the energy of the emitted radiation is same as that used in the excitation. In some atomic and molecular system, the emitted So radiation is of different frequency than that of the excited radiation. So, so these are due to fluorescence or phosphorescence. So that means if the frequency of the emitted radiation is different that of the excited radiation, then that will give rise to fluorescence and phosphorescence. Now coming to Raman spectra. So when a radiation interacts with matter, a part of so when a radiation interacts with matter, a part of it gets scattered, and if monochromatic radiation is used, then the scattered radiation is of the same frequency as that of the incident frequency. This is called relay scattering. So that is called relay scattering. So that means, again I am so repeating, when a radiation interacts with matter, a part of it gets scattered, and if a monochromatic radiation is used, then the scattered radiation is of same frequency as that of the incident radiation. That is called Rayleigh scattering. However, it has been found that in certain cases, the radiation may interact with matter in such a way that it involves certain amount of energy exchange, and consequently the scattered radiation has different frequencies. That means greater or smaller frequency that of the incident radiation. So this is called Raman scattering. So if the scattered radiation having different frequency that of the incident radiation, that is called Raman scattering, and if the scattered radiation having same frequency that of the incident radiation, that is called Rayleigh scattering. So this is another type of spectroscopic technique. So these are the spectroscopic methods used on wavelength range and the type of quantum transition involved. So the first type of spectroscopic method, that is called Mossbar spectroscopy or gamma ray spectroscopy, having wavelength range 0.005 to 1.4 angstrom. So type of quantum transition, nuclear transition, that is change of nuclear configuration. The next one is X-ray spectroscopy, which involves diffraction, absorption, emission, fluorescence, all these things. So that is due to inner electron transition. So that means electron transition takes place. If the electron transition takes place within the atom of inner shell, so if inner shell electron will undergo transition, then that will observe X-ray spectra. And the next one is vacuum UV absorption, having wavelength range 10 to 180 nanometer, having bonding electron transition, that is change of electronic distribution. The next one is UV and visible. So that also include absorption, emission, and fluorescence spectra, having in the wavelength range 180 to 780 nanometer. So that is bonding electronic transition. So the electron will undergo transition from ground to excited state. So these are only bonding electrons, not the inner electrons or core electrons. So if inner or core electrons will undergo transition, that will show X-ray spectra. But if the valence electrons, bonding means valence electrons, if the bonding or valence electrons will undergo transition, that will give UV and visible spectra. Now coming to infrared and Raman spectra. So the infrared due to absorption and the Raman due to scattering. So the wavelength range is from 0.78 nanometer to 300 nanometer, and here the molecule will undergo vibration or rotation, and due to that electromagnetic radiation will absorbed or scattered. And after that microwave absorption spectra. So here the wavelength range 0.75 to 3.75, that is due to rotation of molecules. That means change of orientation of the molecule. Generally gaseous molecules are considered here. The next spectra, that is called NMR, nuclear magnetic resonance spectra. Here the wavelength range is 0.6 to 10 meter. So that is due to spin nuclei in the magnetic field. That means spin of the nucleus. Due to spin of nucleus around its own axis, magnetic field will generate, and the magnetic field, when external magnetic field will be there, the external magnetic field and internal magnetic field generated by the nucleus of an atom will interact with one another, that will give rise to magnetic nuclear magnetic resonance, NMR. And similarly, exactly in the similar way, electrons are also circulating around their own axis, so that will they will also produce magnetic field. And if the interaction of the external magnetic field and the magnetic field arises due to transition of circulation of electron around its own axis, that is the electron spin, that is called, so the interaction of external electric field and spin of the electron, that is called electron spin resonance or ESR spectra. So here in this chapter we have discussed the different types of electromagnetic radiations and what are the different phenomenon, and what are the different spectroscopy observed. So here some terminal questions are there, you can solve the terminal questions. So here some questions and answers are there, and after that we will move to the chapter. So this is the introduction chapter, and after that we will move to unit 2. So the unit 2 is UV visible spectrometry. That means transition of atomic or molecular electronics level from ground to excited electronic state. Hello?
Yes, sir.
Okay, so actually, so today the introduction class are start. So we'll discuss the UV visible spectra from the next class from tomorrow. Okay.
Okay.
Hello. So
Okay,
that will
sir.
discuss tomorrow. Hello.
Hello. Yes, sir.
Okay. Okay.
Hello. 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 Are you done with your assignments? Hello. Hello.